So welcome you all again to this lecture series of multivariate calculus. So in this lecture I will talk about the total derivative. Okay. So let's understand what is the total derivative. Suppose we have one function, let's say z. Okay. So z is one function consisting of two independent variables x and y, and x is another function of phi t and y is another function of psi t. Okay. Now then z basically a composite of function of t, right? Why? Because originally z is a function of x and y. So z is given that z is a function of x and y, but in the place of x, if I write equal to phi t, so it will be basically f of phi t and then y equal to psi t, right? So then this z basically will be function of t only, right? So z will be a function of t only. Now, sorry for this bracket. So we can find out the derivative of this function z with respect to t, original derivative, right? Because it's only involve only one independent variable. So here what we'll do, we can find out the total derivative is called, and that is equal to del d2z dt equals to del z, okay, del z del x into dx dt plus del z del y into dy dt. Now understand each of these term one by one. So as I already told that z is a function of t, if I replace x in the terms of phi t and y in the terms of psi t, then I get the z is a function. So it is z dt. Now z when I as z originally function of x and y, so first we have to partial derivative this one with respect to x into d z dt plus delta z delta y into dy dt. So that is basically called the chain rule. Okay. Now here dx dt, why? Because x is a function of t only and y is a function of t. So that's why it's come your original derivative, not the partial derivative, that is dy dt and dx dt. And similarly here in these two cases, uh, as z is a function of two variable x and y, so here partial derivative comes. So to get the total derivative of z with respect to t, I have to first differentiate the function z partially with respect to x, then into multiplied with the original function x that is involved in t with respect to t plus del to z del y into dy dt. Okay, so this way we can find out the total derivative of this function. Now if I generalize this function, suppose we have uh, a function z consisting of three independent variables x, y and z, and x is equal to phi t, y equal to psi t and w equal to st. Then h you can similarly can say it is a composition of three composite function of t, because if you replace x by this one and y by psi t and z by w by st, then you will get z is a function of t. Then we can find out the total derivative of z with respect to t in this way: del z del x dz dt plus del z del y into dy dt plus del z del w dt, right? So similarly you can generalize this case. Suppose z is a function of n variable, n independent variable. Let's say it is involving of x1, x2, and let's say xn up to xn, and each of these xi is some function of phi t. All of this function of phi t, phi it. Okay. Then you can find the total derivative of z with respect to t in this way: del x dz dt, not del, it should be d. Then partial derivative of f or z with respect to x1 first component, or you can change for this. Then d of x1 with respect to t plus del z del x2, right? And then dx2 dt, and so on. And finally the last one, it will be del z uh, del xn and dxn dt, right? For generalize, you can do this one. And this is all. Now by using this total derivative, okay, another term is that total differentiation. Instead of derivative, it is differentiation. So here we will find out the increment of z. So basically we are dividing out this, multiplying that the dt both side of the previous equation. Then in the previous equation, if I multiply the dt both sides, then it will be del z, and only dz equal to del z del x, and here also dt will be cancelled out, so del x. So that's basically called your total differentiation. Okay, so then you will get this equal to del z del x into dx plus del z del y dy plus del z del w dw, and so on. Now first example of this total derivative, suppose we have this function z equal to x plus y, where x is a function of t, that is e to the power t, and y is a function of t, that is t square. Then we have to find dz dt, and so you know the formula for finding the total derivative, so you can do that this way, right? So it is formula is del z del x into dx dt plus del z del y dy dt. Now del z del x with this, so it will be 1, right? And dx dt, that will be to the power e to the power t, and this is also 1, and dy dt equal to 2t. And by simplification, you will get this one. So this is the total derivative of z with respect to t. Now next example, here we'll find the differentiation. Okay, find total differentiation. So here z involves of two three function x square y z, but it is not mentioned that it is a function of t. Okay, and let's assume all these are function of t. Now we'll find out the total differentiation of this function at this point 1 to 3. So by using the previous formula of the differentiation, I know that dw equal to del z del x at the point ABC into dx plus del z del w del y ABC dy plus del w del z ABC at the point ABC and dz. Now we'll first find out this value del z del x from the given function. So it will be basically 2x yz. The next one del w del y, it will be x squared z, and the last one, that is del w del z equal to x square y, right? Now I have to find out value of this each of these function at the point 1 to 3. So basically I'll put x equal to 1, y equal to 2, and z equal to 3 in this, all these points, all this equation. So at this point I'll get del w del x equal to 12, right? And del w del y equal to 2, and del w del z equal to 3, right? So because 1 and 3 and this is so on. Now ultimately I plugging all this value here in the given equation. This value, I'll get the total differentiation of this function dw at 12 dx plus 2 dy plus 3z. And that's all of this total derivative. See you in the next lecture. Thank you.